Video 5 of Chapter 7, where we will switch gears a little bit with our sampling distributions. Instead of doing proportion problems, we are now going to start exploring mean sampling distribution problems. Now, what do you think is the mean height for a power forward in the NBA? And I got 4 of my favorite power forwards right here. I bet you all can name them all, right? And we got Giannis, we got, what's this guy's name? Is that LeBron? No, that's not LeBron. That's Zion. That's Zion. And then we got, this is Kevin Durant, and that's Steph Curry. Yeah, I know all these guys. I know them all. Yeah. So what do I think the mean height of a power forward is? It's tall, right? It's really tall. Those guys are tall. Taller than me? Taller than you? I don't know. These guys are tall, right? Well, here's the truth. The heights of power forwards in the NBA follow, believe it or not, a normal distribution with a mean of 80.1 inches tall and a standard deviation of 1.5 inches. So 80 inches tall. Geez, what is that? Like 6'6". 6'6"? No, 6'8". 6'8". These guys are giant. They're power forwards. This is crazy. I mean, like 20 years ago, that would be like a center. Center would be like 6'8". These guys are giant. So anyway, we know the population shape, we know the population center, and we know the population spread. We know it's normal, we got a mean, we got a standard deviation. We know the truth about the population. Now, I am 76 inches tall. Fact. What is the probability that we would randomly select a player, a power forward player, of Mr. G's height or less? Now, this is an old school, basically chapter 2 normal CDF problem. And we would have done this and we would have said, let's let, we'll use H for our random variable. Let's call the height of a person H. So what is the probability that a randomly selected person's height, power forward's height, would be my height or less, would be less than or equal to 76 inches? Well, we know the population follows a normal distribution with a mean of 80.1 and a standard deviation of 1.5 inches. So I already know what the shape of this looks like. The mean in the middle is at 80.1, and I got to go down to 76 inches, which would be a little more than 2 standard deviations down. So 76 inches is kind of a far enough distance away, and we want to go or less. So if I were to calculate using normal CDF, and I would go negative infinity or really 0 realistically, up to my 76-inch height, then the mean of 80.1 and a standard deviation of 1.5. What does that, pray tell, give us? So normal CDF. Really, we can start at 0. No harm, no foul there. Get it? No foul. That's a basketball term. What do we say was the height? Or not the height. The mean. 80.1. And the standard deviation was 1.5. Okay. So what's that going to come out to be? We get a very small probability. So what's the probability you're going to pick someone of Mr. G's height or shorter? It's really going to be not very many power forwards that are smaller than me. So I'm not really going to make it to the NBA, guys, as a power forward. So be thinking of me. Maybe I can find a different career. I don't know, teaching math or something. So 0.3%. 0.3%. Not a great chance. Now, you might be wondering, we've been talking about sampling distributions, and this really didn't feel exactly like a sampling distribution. And that would be true. If your sample size is 1, you don't have a sampling distribution. You have the population distribution at your disposal. The only time we really get to talk about sampling distributions is if the sample size is more than 1 and we are calculating some sort of statistic from all of those greater than 1 in our sample. So this is basically an old school chapter 2 problem. We have access to the population, shape, center, spread. We're only dealing with one person, so we can do just a usual old normal CDF problem to calculate this probability. Now, if I wanted to turn this into a sampling distribution problem, then we would have to change the problem to look like this. What's the probability that we would randomly select 5 power forwards with a mean height of 76 inches or less? Now, consider there was not a great probability that you were going to select a power forward at random that is as tall or shorter than I am, right? 0.3%. So what do you think are the chances you're going to randomly select 5 power forwards that have a mean height of my height or less? Hopefully you are thinking in the back of your mind like, well, if one person's only 0.3%, getting 5 people that have a mean height of 76 inches or less. Now, some of those people might be taller than 76 inches, but if the mean height of all 5 people is 76 inches or less, that means we got to have more shorter people than taller people, right? I mean, maybe you have one really tall person, but 4 really short people that are going to weigh out the mean to be 76 inches or less. So we need to discuss now a sampling distribution for sample means. So let's look at some sampling distributions that are based solely on a normal distribution. What if the distribution is not approximately normal to begin with for the population? That'll be something we'll discuss in the next video. So this is the population distribution. You can see it's a nice approximately normal distribution. And what I'm going to do is I'm actually going to create 2 sampling distributions. One of them is going to be based on samples of size 5. And the other one's going to be based on samples of size 16, so that you can see some of those things that we've already discussed at the beginning of the chapter about what happens when our sample size gets bigger, what happens to the shape, the center, and the spread of the sampling distribution. So I'm going to click this animated button, and what's going to happen is first it's going to work on the sampling distribution based on a sample size of 5, and it's going to randomly select 5 from this population. And then it's going to calculate the sample mean of those 5 values, and it's going to give me one data point in the sampling distribution that'll be created right here. And then what will happen is it will do the same thing, but it will take a sample size of 16 from this population distribution. And then it will take those 16 values, calculate a sample mean value, and give me one data point in this sampling distribution. So let's watch it happen. So there's the 5. There's the sample mean of the 5 right here. Here are the 16 data points being taken from the population. And then there's the sample mean right here from those 16 values. So this is like just one person taking a sample of size 5, coming up with a sample mean, and saying, here's the value I got. And then another person saying, well, here's my random sample of size 16, and here's the sample mean of my 16 values. So I could keep pressing this animated button one at a time, and it's going to select one random sample of size 5 and one random sample of size 16. And it's going to keep giving me just one data point at a time. And it's going to take a while before we start to see some features emerge out of these 2 different sampling distributions. So that'll be the last time here that I'm just going to click the animated button, because now what I'm going to do is I'm going to tell it to do 5 random samples at one time. So it's not going to make the fun little animation here in this second sample data area, but it's going to give me 5 new sample means for this sampling distribution based on samples of size 5, and it's going to give me 5 more data points, 5 more sample means for samples of size 16. So there's 5 more, and another 5 more, and another 5, and another 5, and another 5. And so right now, 28 random samples have been taken overall for both of these sampling distributions. And these are kind of like the things that we would have seen during class, right? We kind of saw maybe an approximately normal shape starting to emerge in both of these. Some people might say, well, this one still looks a little more skewed-ish. This one down here maybe starting to look approximately normal. And the key was we would just need to be taking more and more and more samples in order to see those features really emerge. So I'm going to go up to, here's 98. And I tell you what, let me animate 2 random samples. So we'll be at 100 exactly. All right, so there's number 99, and here is sample size, or sample number 100. And after 100 random samples, you can start to see those features starting to emerge here. So there's 100. Now, this applet works by either doing 1 random sample at a time, 5 random samples at a time, 10,000. Like, it jumps huge to go from 5 to 10,000. And then I can also take 100,000 random samples in one instance. So if you notice, we can kind of see those features that we saw earlier, right? Like, it's starting to look more and more approximately normal. The center of each of these sampling distributions look like they're about the same, which looks like it's about the same as the population distribution up here. So that's something we saw earlier this chapter. And as the sample size got bigger, what do we notice about the spread? The variability looks like it is decreasing. So now I want to take it up a notch. Now, instead of just doing 5 at a time, I'm going to do 10,000. And this is going to be a huge jump here. But there's now 10,100 random samples. And now you can really see, oh, there's that lovely, beautiful looking approximately normal shape in both of these. And again, notice the centers are lined up with the population distribution, and we can definitely see that the spread has decreased with the larger sample size being taken here. So when the population is approximately normal, regardless of what our sample size is, if it was a small one like 5, if it's a bigger one like 16, we see that the sampling distributions are also approximately normal. Now, I could, just to show you one more thing, what if I did sample size 2? 2 is the smallest I can take here, and 25 is the biggest. So what if I start off with 10,000? And another 10 and another 10. So there's 100,000 right there. And you can still see that it's definitely looking approximately normal. The centers are lining up with the center of the population distribution, and the spread is getting smaller from a sample size of 2 to a sample size of 25. So again, when the population is approximately normal, and again, you might be wondering, what happens if it's skewed, for instance? Ooh, that'll be something we'll discuss in the next video. So for right now, the main thing to know is if the population is approximately normal, it does not matter the sample size that is taken. The sampling distribution is guaranteed to also be approximately normal. So we learned that the shape of the sampling distribution of a sample mean will be approximately normal for any sample size if the population distribution is also approximately normal. Now, you might be wondering, how am I going to know if the population distribution is approximately normal? The problem is going to have to tell you that information. There is no way that you would be able to just automatically assume that the population distribution is approximately normal. So this has to be told to you in the problem. Okay? Now, what if, because everybody's going to ask, but what if they don't tell us the population's approximately normal? What if they don't tell you the shape at all? You know, what if they just say, well, the population has a mean of this and a standard deviation of this? Can I assume it's approximately normal? No, you can't. Maybe it's skewed, maybe it's uniform, maybe it's bimodal. We don't know if they don't tell us what the shape is. We can't assume that it's approximately normal. So what if the population is not approximately normal, or what if we just don't know the shape of the population? That'll be for the next video. Stay tuned. Now, the center of our sampling distribution, the mean of all of our sample means, ended up being approximately the same value as the population mean. And we saw this happen in class whenever we dealt with the mean ages of our marathon runners, right? The mean, the center of all of our sample means that we came up with, where was the center of that sampling distribution roughly located? And it was roughly right on top of the population mean value. Right? We thought this number was around 39 years old. And what was the truth about the population mean age? It was 38.81. So we may not necessarily say equal, but it's going to be pretty darn close to being the same. Now, the sample mean X bar, all of those sample means that we were creating, can reasonably estimate the population mean mu because, based on video 2, the sample mean is an unbiased estimator of the population mean. So it's great that we can use the sample mean to estimate the population mean. And then for the spread The standard deviation formula is a lot nicer than it was for proportion sampling distributions, but the standard deviation, sigma sub x bar, the standard deviation of all of the sample means that we could create, is just going to be the population standard deviation divided by the square root of our sample size. But notice, we still have the same exact condition that we had for sampling distributions of proportions, if that 10% rule still applies. So is the population still greater than or equal to 10 times our sample size? And a lot of the times we're just going to assume that this is true. Sometimes they'll give us key words, like they'll say from a large company or from a large population, and then we can normally assume that that would be true. So let's now answer the question that we asked originally. What is the probability that we find a mean height of 76 inches or less from a random sample of 5 power forwards? Now, instead of this being h being less than or equal to 76, it is a mean height of 76 inches. So it's not just h is less than 76, less than or equal to 76. It's h bar. This is the sample mean. So it's kind of like we're saying x bar. So this would be the sample mean. And if we want to do x bar, we could certainly do x bar. So the sample mean would be less than or equal to 76. Now, before we get to use normal CDF, we need to go verify what are the shape, the center, and the spread here. So the shape will be approximately normal. How do I know the shape will be approximately normal? Because we were told the population distribution is also normal. And again, what happens if it's not normal? We'll talk about that next video. For the center, mu sub x bar was the same as the population mean mu, and we were told that that number was 80.1. No condition to check here. For the spread, sigma sub x bar is equal to sigma, the population standard deviation, divided by, ooh, that's a crazy n. Let's try it again. Divided by the square root of n. So the population standard deviation was told to be 1.5, divided by the square root of our sample size. Sample size was 5. So what does that number come out to be? Let's see, 1.5 divided by the square root of 5 equals 0.5477. I just want to make sure I'm doing this correct. Let's try this over here. 1.5 divided by square root 5. Oh, yeah, I thought I messed something up there. 0.6708. 0.6708. And again, I got to check. Is the population, are all power forwards greater than or equal to 10 times my sample size of 50? Are there more than 50 power forwards in the NBA? And you might be like, well, I don't know anything about power forwards. How rare are they? There are definitely more than 50 power forwards. So I will tell you that is a true statement. So now, to answer the probability question, I do get to use normal CDF. And if I wanted to see a nice picture here, the mean in the middle is 80.1. 76 is going to be very far away, if you want to figure out how many standard deviations that is. And we are going less than it, again, less than or equal to. So the lower bound, theoretically negative infinity, realistically 0. 76 is our upper bound. Mean 80.1, standard deviation 0.6708. How rare is it? So let's jump back to here. Let's go grab our normal CDF command. So I'll just say 0, 76, 80.1. Ooh, what was that number? 0.6708. 0.6708. And we get, ooh my, 4.935 times 10 to the negative 10th power. Ooh. So 0.0, 2, 3, 4, 5, 6, 7, 8, 9, 4, 9, 5, 3, or you could write it in scientific notation. I would be perfectly fine. 4.953 times 10 to the negative 10th power. So would you be shocked if you could find 5 random power forwards that had a mean height collectively of Mr. G's height of 76 inches or less? Absolutely. That is going to be like almost winning the lottery type of example rare. Now, I have a problem for you to try. A bottling company that will remain unnamed uses a filling machine to fill plastic bottles with soda. The bottles are labeled to contain 300 milliliters. The soda dispensed into the bottles vary according to a normal distribution, with a mean of 296 milliliters and a standard deviation of 2 milliliters. Describe the sampling distribution of the sample mean based on a random sample of 10 bottles. So I just want you to determine what are the shape, center, and spread of this sampling distribution. You don't have to answer any sort of probability question because that's what we will do the next day in class after we verify that we have correctly identified the shape, the center, and the spread. Good luck.